Hello and welcome back to the Dragonfly Daily. I am your host, Mike, the product manager at ORS, working on the Dragonfly product. We are back for lesson 11, image filtering. So lessons 11 through 14 will all be on image processing. Today's lesson is on image filtering. As always, go and find me on Twitter if you want to hear the updates and when these are posted to YouTube, but also upcoming lessons and other content. Follow me. And also, if you're watching this on YouTube, hit the subscribe button right now. That way we know that you guys want more content. Now let's dive into image filtering lesson. This will be done with Dragonfly 4.1. The tools that we're using are Dragonfly 4.1, slightly customized experience as described in lesson 6, customizing Dragonfly. So the topics we will, there's always something wrong with this slide. This slide should say image filtering. Let's fix it right now. Can't look at that too long. So this lesson is on image filtering. On today's lesson, we will cover a few topics. We will give some examples of image filtering, including smoothing or denoising, edge enhancement, a little bit on artifact correction. We will talk mechanically about how you do the image filtering in Dragonfly. So this operates in its own context. You'll see what I mean. We'll look at how you set the image filter, choose the filter, choose the parameters, choose the inputs, the outputs, etc. How you can preview the filter. You'll see why you get to benefit from a synchronized pan, zoom, and window leveling when you're inspecting the filter. We'll also look at the advanced filter parameters, which is really about changing the output type. Then we'll look at stacking multiple filters or running multiple filters in a queue in sequence. Then we'll look at when you're doing outputs, how to keep or discard the outputs of image filters. All of this will make sense after we've gone through it once, and then saving filter parameters for later use. And later use means you'll be able to use image filtering in the main context. With that, I should tell you what data we're going to use for today. We will be using two data sets. The first data set is the one we used in one of the previous lessons. I believe, well, it doesn't matter what lesson it was. Let's pop on over here. The data set we're going to use is Christopher Bleck's rod internal segments data set. You can really do this lesson with any data. It's just going to show you how to preview an image filter. But the data set we're using, of course, if you go to ORS Dragonfly, point Google there, you'll find our homepage. From our homepage, if you go to Learn and Sample data sets, the first data set we'll be using is this one, the segmented mouse retina cells. So you can grab this data set. That's what we'll be using initially. Then we will also use a data set that is available online, but we don't have permission to share it. And this is the ISBI 2013 Challenge data set. So if you read this page, you will find that you can register and make a request to the data set. If you looked at the Twitter announcement of the Image Processing Week lessons, you'll see that there's a data set of some SEM images of neurons, and they show some brightness artifacts. And so we obviously wanted to show you that you can correct that in Dragonfly. We don't have permission to share those data set, those images, but you can grab those Lichtman Lab data from this website. So you can just point your Google browser or point your Google search to ISBI 2013. All right, the first data set I'm going to work with is the mouse retina cells. And so this is what I shared last week. So, I moved it. Where's my mouse retina data? Segmentation demo. Oops, wait, maybe, give me one moment. Let me browse. Mouse retina, here we are. So and let me resume. So once you find that data set, you can choose it. And then we don't need the mitochondria. We just want the image data and maybe the acknowledgements. So just as a reminder, these data come from Christopher Bleck's group at the NIH and NHLBI. So thank you very much, Christopher, for these data. Now, once you have a data set loaded in Dragonfly, actually, yeah, that's good. Once you have a data set loaded in Dragonfly, you can go into the image processing toolbox, or what we call a special context. You'll find this in Dragonfly 4.1 under the tools menu. Go to image processing toolbox. Here, you'll see this new context. I'm going to grab this image processing panel and float it right here. This is a context. We'll also see this in lesson 14 or lesson 15 on doing stack alignment. You'll notice, I think it's lesson 14, you'll notice that we don't have all of the normal control panels or the menu bar. This is sort of a restricted or constrained workspace for accomplishing a specific task. What I can do here is I can focus mostly on the image processing panel. Now here we have on this drop down a list of operations, and they are categorized. So here are some topics, including in the topic. Here are some image filters in the category arithmetic. Here is an image filter in the category artifact correction. So the blue labels are the category, and then you have filters in that category. Now, the first category that people often want to do in enhancing images is they want to denoise their image. Technically, these should be called smoothing operations, and so that's where you'll find them under smoothing. So these include like Gaussian smoothing and median smoothing. Let's start by just scrolling down. I'm using the mouse wheel to scroll down. I'm in segmentation, I'm in shading compensation, I'm in sharpening, smoothing. Now here in smoothing, we could, for example, choose Gaussian. Now, I have pulled up the Gaussian filter, and what immediately Dragonfly does is if you have multiple image channels loaded, it's going to prompt you to choose an input for the image filter. Now, in our case, we only have one image channel, so it automatically populated. And it's going to create an output name for the image filter. Right now, it's just the same as the input name -Gauss because this is a Gaussian filter. Now, if I wanted to denoise this image, and let me discuss what I mean by denoise. If you scroll through here, you can see that these are all of the resin pixels, and we might assume that they're about the same electron contrast, but some of the pixels are a little bit darker, some are a little bit whiter. A smoothing or a denoising image would help smooth those over. Gaussian is an example of such a smoothing filter. Now, what you can do is you can set the parameters for this filter. Do you want it to operate in 3D or 2D? So maybe I choose 3D, and maybe I just choose the default kernel size and the default standard deviation. What I could do right now is I can click Compute Selected Preview. And on the right, we have a preview. Now, it has created a preview of this single image slice 226. If I scroll to another slice, I don't have any previews. The preview is only computed for slice 226. What you'll also notice is as I zoom, I'm using a middle mouse drag to zoom, and as I pan left and right, drag, I'm seeing the input image and the output image. That's thanks to Scene View's synchronizer. So it's set up so that if you drag in the view on the left, it will update in the view on the right. So as you can see, if I zoom in, you'll see that these pixels are much flatter. There's less statistical variation, so it has been smoothed. That is the behavior of a smoothing filter. Now, some image filters will take a long time to compute. And so perhaps you're trying to decide what filter to use, and you don't want to run the entire filter on the entire image stack and maybe take 5 or 10 or maybe even 30 minutes before you realize you don't get good results. So the behavior here is you choose an example slice. So in this case, we chose slice 226. We go to another slice. You choose a slice and click Create Compute Preview. If you don't like the parameters, you can change the parameters and click Preview again. It only computes the filter on the area that was visible at that time. So you can save yourself time rather than computing on the entire stack or computing on the entire image. You compute on one small area. So you have that luxury of it being able to experiment with parameters. Then once you have filter parameters you like, you can click the apply button and it'll apply on the entire stack. Now, a few moments ago, I mentioned that the Scene View synchronizer is synchronizing zoom and position, and so I'm having this. Now, if you know your shortcuts for controlling window leveling and you want to change the brightness on the image on the left, it is not synchronized unless I have the image panel on the left selected. I click the WL, and now it will change the brightness and contrast or the window leveling in a synchronized way. So now I have pan and I have zoom and I have window leveling synchronized. So this gives me an environment where I can test out the image parameters, see the before and after, and see if I like what I see. Now the Gaussian was an example, a very common example of image filtering. One of the things people don't like about this smoothing filter is that it tends to blur edges. You may have structure and detail and you may lose that detail because it gets blurred out by a Gaussian filter. I'm going to show you another example smoothing filter. This one, like Gaussian, this is in all of the textbooks. If I change my image filter operation at the top and I change it to median, and let's just use the default parameters and click Compute Selected Preview. So the median filter, it's very good at removing something that's called salt and pepper noise. We don't have time for a real proper image processing lecture here, but it can be computationally expensive, especially when you apply it in 3D and have a big kernel, but it doesn't tend to do as much blurring of the edges as a median filter. Now, one of my favorite filters is the mean shift filter, so I can choose the mean shift. This image channel has intensities from 0 to about 255, and so normally I'll plug in that. I'll plug in 255 in this parameter for noise spread, and then I can do Compute Selected Preview. This is the mean shift filter. I like it better. I think it doesn't do as much blurring as the Gaussian filter, but those are 3 different smoothing filters. Now, suppose you wanted to compare on the same slice 3 different filters. What I could do is I could set up 3 filters. Let me show you. I have one filter here, which is the mean shift filter. Now, suppose I add an operation. Now, if I now choose the Gaussian filter, so I'm going to scroll down, I'm going to go to smoothing and choose Gaussian. Now, Dragonfly assumes that you want to do a sequence of filters, and so it's setting up the input of the Gaussian filter. It's calling it image-mean shift. It's actually setting it up to be the output of the previous filter. Now, in this case, that's not what we want. We want to apply the exact same input. So I've got a Gaussian filter, and now I will add a third operation, and this operation will be the median filter. So I'll scroll down, or I can just type MEDI, and I pop up, whoops, I misclicked, so a little fast on the mouse, choose median. Now, what I can do is I can make sure that these are all set to the same input, and then I can do compute all previews. Now, when I do compute all previews, it's going to take the currently viewable slice, and right now I'm looking at a preview of the median filter. If I click here, I'm going to see a preview of the Gaussian filter, here of the mean shift filter. So you can zoom in and pan and compare the results of these filters to see if what you like. Or you could run the same filter with 2 or 3 different sets of parameters all dialed in here. So that is the capability of doing multiple filters, and these are all filters that are run, and they're all run, but they're not dependent on the previous filter. Now, let's do a different example altogether. I'm going to click this X and this X. Now I'm going to take the first filter, and in this case, I'm going to show you running 2 filters in sequence. Suppose I want to do edge enhancement, and edge enhancement can be done with, among others, the Sobel filter. So if I type S-O-B, Sobel is right there, and I click it. So if I just take the Sobel filter, which it occurs in this list of edge detection filters or edge enhancement filters, if I take the Sobel filter and I click Compute Selected Preview, over here it's quite dark. I'm going to unclick Window Leveling, and I'm going to drag up the brightness. Okay, so I'm seeing just the edges of the image. But there is some noise here. I'm seeing the edges, even though there's very little structure here, it's picking out some edges. Maybe I want to smooth the image first. So if I were to choose a smoothing before the edge detection, so if I go down and I choose, for example, the Gaussian again, if I choose Gaussian and maybe I use a bigger kernel size, and then I add an operation, and this time I choose the Sobel, S-O-B. So Sobel is chosen, and now it's taking the output of the previous filter, output of the Gaussian, as the input to this filter. So what'll happen when I do compute previews is it'll take my initial input image channel, it'll pass it through a Gaussian, then it'll take the output of that and pass it through a Sobel. So now I can run compute all previews, and over here is the output of the Gaussian. So, you know, it's just a Gaussian smooth. And if I click here, I'll see the output of the Sobel. So a little less structure here. So this allows me to run images in sequence. Now, supposing I wanted to run this sequence of filters and all I really wanted was this edge enhancement. And so I have computed the Gaussian, and then I've used the output of the Gaussian as input to the Sobel. So I've done these image processing operations in order to get a smooth and then edge enhanced image. Now, maybe when you run this on the entire stack, you don't care about the intermediate output, this one that is the Gaussian. You only care about this. Come down here and look at output. This is saying right now there are going to be 2 outputs when you hit the apply button. It will create a new data set for the Gaussian, and then it'll take that and it'll put it through the Sobel, and it'll create a new output. If you only want the final output, you don't want the intermediate, you can just click this X button. Now when you hit apply, it'll still do the filtering, but it'll only keep this one. This create data set, you could tell it you want to overwrite a data set in memory instead of creating a new data set. So that's what this drop down is for. So what we've looked at so far is we've looked at the 3 different smoothing filters, sort of the Gaussian, the median, the mean shift. Those are just different filters for smoothing. And then we've looked at being able to do the preview on all 3 simultaneously with the compute all previews. If you were only to choose compute selected preview instead of compute all previews, you're just going to get the preview for this, not for both. So, and then we've also looked at smoothing followed by edge enhancement. So that gives you some idea of filters. Now, there are dozens of filters implemented here, and users can implement their own filters as well. Now, the other filter that I want to show you today is the one that compensates for maybe inter-slice brightness variation. Now, let me load a new data set to show you what I mean. Now, inside the image processing context, I don't have my normal menu operations over here for like choosing file, input image data, but I do have input image files here, which will open up the regular import datasets dialog, and I also have the import button here. So I'm going to click this button over here, and I'm going to say I want to input neocortex serial section SEM, and I will input both. And over here on the left, I'm going to, let's remove a filter, and let's choose a, well, it doesn't really matter what filter I choose, but let's just choose a neocortex input. And I'll drag this out of the way so I can put on this attribution. So these data, again, are from the ISBI 2013 challenge, which is data produced by the Lichtman lab on this neocortex sample. I don't know the serial sectioning method, if this is like array tomography or some other 3D technique. But if you look at this data set, you can see that as we scroll through the samples, sometimes they're a little bit brighter, sometimes they're a little bit darker. And so that's something we might want to create a solution for. Now, in Dragonfly, that's an example of one where you can't get very good results by doing a preview, but I'll show you what I mean. Let's see. All right, so this slice is a little bit brighter than, this is slice 26. It's a little bit brighter than slice 27 or 25. So if I went to slice 26, and over here, I scrolled through the image filters, and near the very top is artifact correction, gradient domain fusion. If I ask for a preview on just this one slice, then it'll create a preview. And over here, it's a little hard to tell because you're not looking at it in context. So this is really hard to do an effective preview on this data set, because a single slice is not really telling. I'm going to go ahead and let's make sure there's an output specified. I'm going to tell it to go ahead and apply the entire 100 slices. I think my Zoom meeting will hold up. This is going to consume some of my CPU. This is going to take about 60 seconds on my laptop to do these 100 slices. So now I'm just going to keep talking and pretend like I have something to say while this image filter operates. So this is, as I say, one of those image filters where you can't get very much information just by doing a single slice preview, but you can do the apply operation here inside the context, or I'm going to show you in a few minutes how you could have this filter saved and you could apply it from the main context. But the overall idea is you can apply the filter, have a whole new image stack. So if your input image stack is 100 slices tall, then your output image stack will also be 100 slices tall. So everything I've done before now in today's webinar, I've been computing previews. This time I hit the apply button, and so it's applying on the entire 100 slice stack. And now I've run out of things to say. After we look at this, we will look at how to save image filter parameters so that you can then export those image filter parameters and access them from inside the main context without having to come into the image processing toolbox. That can save you time. This is really the area where you sort of evaluate and test filter parameters, but if you already know what you want, you can call it up at any time. Okay, the window on the left is showing our neocortex input. The window on the right is showing our last preview, but if I click over in the window on the right and I turn on the visibility of the last output, now I can scroll through the slices, and I think you can see even in the Zoom transmission, you can see that the slices on the left have variable brightness and the slices on the right have normalized the interslice brightness and even some of the variable brightness across the slice. So that's the behavior of that gradient domain fusion filter. Okay, two more topics I want to cover in today's webinar, and then we'll be done with the content. The first topic is there is an option on all image filters to click Advanced Options. This allows you to specify the bit depth of the output data set. So if the input data set is an 8-bit, it's probably going to generate an 8-bit output, although some image filters will generate a floating type output. But you can override this and say what you want the output to be. You can also say that I want the image channel to be in a particular geometry. So this is a bit nuanced, but if you had done like used one of those boxes to extract structured grid and you wanted to do the output in the shape of that new box rather than the input, rather than the box of the input image, you can specify sort of a target image geometry. But most of the time we just choose default geometry. So that's advanced options. Now, if we revisit the scenario we had a few moments ago where we were doing smoothing followed by Sobel. So suppose I come down and I choose Sobel. I'll just type SOBE, and there's Sobel. Oh, you know, I made a mistake. I wanted to do Gaussian followed by Sobel. So let's say I go to Gaussian and I choose a 3D Gaussian, and then I add an operation for a Sobel, SOBEL, and I apply it in 3D as well. Now, what I can do is I can say I wish to save this sequence of operations as my Gauss Sobel 3D, and I'm going to save it for all users and click Save. Now, we'll see that in just a minute. Now, let's say I really like the mean shift image filter. I use it all the time. Let's say I type mean, scroll down. Here is, whoops, I'm the wrong mean. Let's go back up here, mean shift. Let's suppose I like mean shift, I use it all the time, and I want to have a mean shift that uses this kernel size 5 and uses an image spread of 255. Now, if I do save ops and I call this mean shift 255, I'm gonna put an underscore here, I think you'll see why in a minute, and I do save. Now, the parameters of this image filter are in fact saved. So if I know I want to use this filter again later, I don't need to tune the parameters, then that means I don't have to come back into image processing toolbox. I can actually employ it from the main context. And let me show you how right now. In order to leave the image processing context, you can either click the close image processing here, or you can click this X up here. It's probably makes you feel a little more comfortable, just click this button. I think the first time you do that in Dragonfly, it may make the screen disappear. But anyway, here's my main context right here. Now, what I can do is if I come over on the left on the main tab, you will find image processing. Over here, I'm going to undock this. And I can choose the input data set I'm interested in filtering, and then I can choose a list of operation stacks. Now I need to hit the refresh, and now I'll see mean shift 255, and I'll see Gaussian Sobel 3D. So if I choose this and I click apply, it will apply this sequence of operations, and it will run them and give me a new output. So this gives you a capability of using those image filters without having to retune the parameters. If you click advanced, it'll just take you right back into the image processing toolbox so you can edit it further. So this allows you to call up that image filter. The reason that this image filter has all of these characters like this at the very end, suppose you have created a set of filters and maybe you just call it smoothing and you want to share that with others. You can put smoothing in the infinite toolbox so other people can access your set of parameters. And maybe someone else puts it in the infinite toolbox, or maybe you share it with a colleague and they already had a filter called smoothing or a filter stack called smoothing. This makes sure it'll have a unique file name. They can both coexist and there'll be no name collision. So it's just this long string of characters. And if you have two smoothings, then you may say, oh, the smoothing I want is smoothing and it ends in 5AAD as opposed to some other smoothing. I mean, you can avoid all of this just by having a unique name, but this solves the problem in case your name is not truly unique. All right, that includes everything that I had in mind. Yep. Everything done. That's everything we were going to talk about for today's agenda on image filtering. So thank you for your time, and I hope that helps you. Now, we will dive into questions and answers at this time. All right. Thanks, Morgan. That's good to know, and I'll have to look into that. Now, Parmesh asks, what do I mean by image stitching? So the lesson, let's say 13, will be on 3D image stitching. That's where you have multiple 3D image channels and they overlap and you want to combine them into one image channel. So if you had something in the micro CT scanner and you did a 3D scan and then you moved the stage up and did another 3D scan and you want to blend them or stitch them together. Okay, next question. Where do you find more information about the mathematical details behind each of these image filters? That's a great question. So in the help documentation, you'll find usually some introductory material on the filters and often a reference of where they come from. So a lot of these filters come directly from publicly available libraries such as scikit-image and scikit-learn and the numerical Python and scientific Python libraries. So if you have questions about the filters, we can give you additional information, but you'll often find information on those references. Next question. Okay, Sarah says she has a pretty hard one for 3D stitching. So go ahead and send me a couple of snapshots, Sarah, and we'll see if it's something we can use for the tutorial lesson later this week. Does image stack alignment work for aligning 3D images in a time series? That's a great question. Actually, we have a separate tool. So there's this is nuanced, but there's aligning multiple slices of a stack in 3D. That's our stack registration. There's aligning two 3D volumes that may overlap and then stitching them into one 3D volume. And then there's a separate task of aligning the same 3D volume, but from multiple time points and concatenating that into a 4D. We do have that. I don't have a lesson planned on it, but it's pretty easy to use. You align the images with the same registration tools, and then you select them all and right click and say create 4D data set, and then you get to choose the order in which the data occur, which is time slice 1, which is time slice 2, etc. So it's probably easier to do in Dragonfly than anything else. Parmesh asked if there is a 3D bilateral image filter available. There is a 2D bilateral image filter available. I don't think it's available in 3D. I think that comes from Scikit Image. The next question is, can we change the boundary conditions for the filters? You cannot do that without writing your own image filter. So that's the short answer. Next question, please explain the kernel size selection briefly. So the kernel size, and you'll find this in any introductory image processing textbook. I don't know if there is such a thing as an introductory image processing textbook, but any digital image processing textbook will discuss kernel size. And every pixel is computed with more traditional image filters. Every pixel is computed as some function of the local neighborhood of pixels. Well, what pixels contribute to that neighborhood? So is it just the pixels, that pixel and the pixel on either side of it, or is it that pixel plus the pixels in a 5-pixel radius? So that is what is specified by the kernel, both the shape and the size of the neighborhood. Now, the next question is about the non-local means denoising filter. So Alexis asks if you can do non-local means denoising in Dragonfly. Non-local means is a special case where it uses not just a local neighborhood, but it uses non-local pixels that have similar statistical neighborhoods. So the Dragonfly does not have the non-local means filter. It is available in Dragonfly Pro. So everything we've looked at in this entire tutorial series is possible with Dragonfly, but there are a few tools, a dozen or so tools that are available only in Dragonfly Pro, and we don't sell that directly. That's sold through Zeiss microscopy sales channel. So if you need the non-local means filter, you can check in with your Zeiss sales rep. However, I will say the mean shift filter is a very strong filter, and you might try it before you decide you need the non-local means filter. Okay, the next question is, what will the filters change the results of various calculations like porosity, aspect ratio, etc.? Yes, your whole objective in doing image filtering normally is to clean up the image so you can get a more, let us say, accurate segmentation. So if you're segmenting based on intensities and pixels are noisy and they're leading to false positives or false negatives because you're segmenting noise improperly, then that's going to give you miscalculations for porosity and aspect ratio, etc. However, it's a tricky game to play because there's usually no ground truth, and so you don't know if your image filter is helping or hurting, but we're just using our visual cortex and our interpretation of the image. But yes, certainly the image filter is going to influence your calculations, and that's what you're hoping to do, is to get a more robust calculation. Jamie asks, in the Sobel filter, what is apply Gaussian before Sobel option? Does that save us the smoothing step? Yes. So there is a parameter in that filter, not where you set a kernel size, but where you just enable a checkbox to apply Gaussian. I think it's a 2D Gaussian, but because the Sobel tends to emphasize noise, it's assumed that a lot of users will want to do a denoising step, and that's why Gaussian is built right in as an option. So a lot of what I did, you wouldn't have to do if you just used that checkbox, but you can compare those results on your own. The next question is, can you apply gradient domain fusion to a 4D data set that has different brightness among the different data sets? That's a great question. We would actually use a different tool. You can right click on a 3D image channel and tell it you want to normalize its histogram with respect to another 3D image channel. That's done in the main context. You don't have to be an image filtering tool. So the gradient domain fusion is not the filter you would choose for that. If you have a 3D stitching example that you want to share that has different brightnesses than either as 4D, well, I guess it's not a great example since it's 4D. But yes, you can try that. Try the right click and normalize histogram. Next question. Can you only correct for brightness differences between slices or also within one slice? For example, fossilization can cause the exterior of bones to be much darker than the interior. I don't see I think I don't quite understand the question, Annika. The filter applies to most of these filters operate on a single slice. Some operate with a 3D kernel, so they operate on a slice with a 3D neighborhood. So some of the filters are 3D and some of them are 2D, but they don't operate on select slices and they don't operate on select areas. You will see when we release Dragonfly 2020.1 that you can dial in the filter parameters and then say, I wish to apply this filter only to slices 7, 33, 57, et cetera. You can set what slices to apply to with the next release, but I don't think that helps you. So maybe we can take that question offline, Annika, in our next web meeting and see what you mean, what you're trying to solve with the fossilization in the exterior of bones. Next question, after you use the filter, how does it affect the 3D image? Well, you can see for yourself, but after you've smoothed it, your image will look smoother in 3D. If you've done an edge enhancement filter, then you'll just see the edges in 3D. So it will create a new image channel in your workspace and you can inspect it just like you'd imported a new image channel directly from your disk. Next question, I have high absorption in my data by metal inclusions. Is there any filter you recommend? That's a great question. I'm sorry, the short answer is no. So the physics of X-ray CT imaging and the math of the reconstruction is causing these streak artifacts you're seeing, and I do not know of any good filter that solves that problem. Some of the medical CT equipment, I'm talking about like a GE CT scanner or a Siemens or a Philips. Some of those software tools, they have $100,000 filters that they use, but they're not simple filters and they're not available in sort of research grade tools. So I don't have an answer for you. The best answer I can give you is we're releasing an advanced CT reconstruction engine about a year from now that will greatly solve problems like this, but I'm sure that's too long for you to wait if you've got research problems in front of you right now. So no short answer for you, I'm afraid. If anyone wants to contribute any thoughts on that, we can bring it up again later on if anyone has any thoughts of what they think are good solutions for dealing with metal inclusions. Next question, can you go through anisotropic filtering? It hadn't worked for me before. Melroy, why don't you send me an email? Maybe there's a bug and there may have been a bug and it may be fixed. So why don't you maybe tell me the sort of thing you're trying to do or send me a slice and we'll work it out and make sure the anisotropic filtering is working for you. Okay, next question. Oh, there were some responses to Melanie. I think you need beam hardening correction filter for CT reconstruction. That's true. If you do have a CT reconstruction engine that knows how to address that, you could turn in the options. And some people say maybe byte scaling the histogram. I'd be interested to see if that would work. I don't understand why it would. So lots of feedback there, Melanie. You can see if any of that's useful. It's a hard problem. I don't dismiss it. I just don't have a good answer for you. And last question, Federico asks, the laptop meets all of the requirements except RAM. This means, and it's a question about deep learning. This means I would not be able to perform deep learning at all, or it'll be slower or limited to a 4 GB data channel. I think you will be able to do deep learning. I think yes. So you'll have maybe more responsiveness on a system with 16 GB, but I think my takeaway is that if you want to do some deep learning examples, actually, I don't know why I'm equivocating. I'm certain you can do deep learning examples with 16 GB of RAM because that's what my laptop that I'm sitting at right now has, only 16 GB of RAM. So it's not a best performance solution, but it'll be usable and you'll be able to do deep learning and be able to work through some examples that we look at next week. All right. Great. Thank you all for your time. Thank you for your questions and answers. As always, hit the like button if you're watching this on YouTube right now, and tune in tomorrow. We'll continue image processing lesson, and we'll talk about some image processing operations like convert and invert and resample. So all that tomorrow. So thanks, everyone. Have a good day. Stay safe and be healthy.